Welcome to the video lecture series on digital signal processing. In this video lecture, we can see about what is discrete Fourier transform and what is its application in signal processing and why we go for a discrete Fourier transform. So, first of all, what is discrete Fourier transform? It is a powerful mathematical tool that helps in analyzing the discrete time. From the name itself, it implies discrete time signals, and it is helpful in analyzing finite duration signals in frequency domain. It's purely discrete. It is not. It is more suited for the digital implementation. Let me explain what it exactly is going to do. Let us consider this is a sinusoidal signal. Can you see how many sine signals here? The green color one, the red color one, and blue color one. It is, for example, x1 of t, which is blue color. It is a 5 kilohertz 2 volt signal, sinusoidal signal. Let us take green color one, which is having the amplitude of 3 volt. It is 1 kilohertz sinusoidal signal. Third one is red color, which is again 2 kilohertz 5 volt signal. So it is the quantitative values are represented here. All the three signals are available here. On just seeing this signal, can you directly say what is the frequency and its amplitude? It is little bit hectic, right? But can you see this frequency domain representation, magnitude spectrum? On seeing this, you can say at 1 kilohertz, 3 volt frequency sine signal is there. At 2 kilohertz, 5 volt sine signal is there. And similarly, at 5 kilohertz, 2 volt signal is available. From the magnitude spectrum, we can understand the frequency easily. Similarly, the nature of the signal can be understood from the phase. So that's why this discrete Fourier transform is used. For doing this transformation from the time domain to frequency domain, we always use discrete Fourier transform. So formula for this is x of e power j omega is equal to minus infinity to infinity x of n e power minus j omega n. For every forward representation, inverse representation is also possible. So, what is omega? As the frequency omega is continuous in the range of 2 pi radians. We always know it starts from 0, the single rotation, it is 360 degrees, so 2 pi radians. So, for n is the number of samples in the range of 2 pi, then k helps in representing the samples. For example, k0, n minus 1 samples are there in the frequency domain. So, while representing 2 pi by n into k times, we represent like this. So, that's why the formula for DFT pair is to get the frequency domain representation x of k, it varies from 0 to n minus 1. X of n e power minus j 2 pi nk. So k value. So when n represents the time sequence, k represents the frequency domain sequence. Got it? Both will range from 0 to n minus 1 only. Similarly, inverse DFT formula, IDFT formula is 1 by n 0 to n minus 1 x of k e power minus j 2 pi by n n k 0 to n minus 1. Both will range from 0 to, because one is in time domain, another is in frequency domain. Let me explain how same sinusoidal sequence with amplitude 1 for 4 samples and for 8 sample how it is created. For 4 sample, this is sample 1, sample 2, sample 3, sample 4. So when we go for calculation using the formula that is given here, frequency domain calculation, we'll get the magnitude spectrum and phase spectrum for the given sine signal. So magnitude spectrum represents at 0 kilohertz is 0, at 1 it is 2 volt, it is again 0 and it is 2 volt. Phase is 0 degree, 90 degree, 0 degree plus 90 degree. So from this, sine wave at one sampled at 4 kilohertz, that is Fs sampling frequency is 4 kilohertz, has two equal components that k is equal to 1 and k is equal to 3. That is n minus 1. Magnitude is 2 volt, phase is minus the 90 degree at k is equal to 1 and 90 degree at k is equal to 3. Got it? Similarly, for 8 samples, we can see See, eight samples starting from zero. The amplitude is 0.701, 7071, 1.8878 is C. Eight samples, let us take like this. It's not 8871, it's 0.707, which is given in the table. You consider this. It is a printing error. So if you find the magnitude, you will get like this 00400, and again it's 74. So this is the phase spectrum, minus 90 plus 90. So from the phase spectrum, we can understand the nature of the signal. Here also you can understand that x of 2 is equal to x of 6. That is nothing but it is equal to n minus 2. So sine wave 1 kilohertz sampled at 8 kilohertz frequency has two equal components at k equal to 2 and k equal to 6, which is nothing but n minus 2. Magnitude is equal to 4 volt. Phase is minus 90 degree at k equal to 2 and plus 90 degree at. So all this information we can calculate using the formula that is given here. X of k is equal to 0 to n minus 1, x of n e power minus j 2 pi n k. When we substitute the sample values that is coming here, this sample value 0, 1, 0, minus 1, we'll get this answer, this magnitude 0 to 0 2. That is, we'll be getting in complex form. If we find the magnitude, we'll get this. If we find the phase using tan inverse of b by a formula, we'll get the phase spectrum. Similarly, if we go for 8 sample and if we go for applying this formula, we'll get these values, magnitude values and phase values, or the application of the formula in finding out the values for the magnitude spectrum and phase spectrum we can see in the future video. Thank you for patient listening.